So if we look back a little, just a little, at 8.2, in 8.2, we were talking about binomial distributions. So we'd have something like, how about 63% of the population agrees, or I don't want to say agrees, I'll say supports a new city policy. Now, if you could get everybody in your city to vote, then the 63% would totally pass it. But we only really expect to get of our city, we only, it's a city ballot measure. So we only really expect let's say 1,000 people to vote. So let's make the assumption, it's a gross assumption, but let's make the assumption 1,000 random people are vote or are polled. Let's say polled. It's not how you spell polled. Random people are sampled. Now we know when we sample this 1,000 people, we're not necessarily going to get exactly 63%. We know that the random 1,000 people that we sample might end up being, just by chance, a little bit more supportive or a little bit less supportive as a group. So if we asked a question like, what proportion of the 1,000 people let's start that way, do we expect to support the policy? Let's start there. So decide what you think that expected value is. Then we'll look at ranges. We'll look at within what range do we, within what range should our sample proportion fall? And I'm going to say usually fall. Now that first question is interesting. It's either it's one of those questions that seems, is it an easy question? Is it a trick question? People can make a big deal out of it. Now, you remember we talked about expected value as a way to talk about a mean when we're talking about probability distributions. So we're essentially being asked, what is the mean proportion of these 1,000 people? But if we kind of don't, without overthinking it, if 63% of the population supports this policy, what proportion of our sample would you expect to support the policy? What do you think?
%63%.
Yeah, both. Kim, you said it with a very 63%. Kind of a question mark at the end. Allie, you typed it with a question mark on the end. It's a lot of commitment to your question mark to type it. But yeah, 63%. Now, it might not be exactly 63% when we sample it, but we expect it to be 63% because it's supposed to model our population. And that's, you know, what we talked about yesterday in terms of when we distribute our possible 1,000 people samples, the mean of that sampling distribution is going to be that 63. We expect most of our sample proportions to be near 63, less further and further off, with an expected value, a mean, a center at 63%. We often say the mean of the distribution of proportions is that true proportion, P. Well, why do we say that? That can seem like kind of a weird formula, always kind of a weird argument, but think of that expected value instead of thinking about what's the mean of the sampling distribution of the sample proportions. That sounds like a complicated question. But if 63% of the people support this thing, how many of our sample do we expect? Well, we expect 63%. It's just in our language, it makes it sound like it's a more complicated question.
But wouldn't you need to know the percent of the population that 1,000 is?
You would need to make sure that that 1,000 is not more than 10% of the population.
Okay.
If it's under 10% of the population, you don't lose independence. So that's kind of the threshold. If you're sampling more than 10%, it's a problem. But other than that, it doesn't matter. Fair?
Yep.
As long as they are truly randomly elected, which is hard. Now, when we talk about what range should our sample proportion usually fall, what do we associate with usually? Just like expect has
one
a technical
standard
meaning.
deviation.
Nah.
Two?
Two standard deviations. Two standard deviations is what we associate with usually. One standard deviation is typical. 3 standard deviations would be almost all. So if we ask within what range should all of our sample proportions fall, we'd go 3. Typically fall, we'd go 1. Usually, we'll go 2. So, but because this is a sampling distribution, the standard deviation, we have a special name for the standard deviation of a sampling distribution. What was that special name for a standard deviation of a sampling distribution?
Standard error.
Standard error. So 2 standard errors from the mean. So our mean is the 0.63. We're going to be adding and subtracting 2 of those standard errors. We just got to remember how to find standard error. Now we had 2 formulas for standard error. We had the population standard deviation divided by the square root of the sample size. But that was for a distribution of means.
Okay.
We're not distributing means here. What are we finding from our samples? we're finding proportions, right?
Okay.
So the standard error for a distribution of proportions is the square root of the probability of success times the probability of failure divided by the sample size. That thing's the square root.
Oh,
So that's the difference between our distribution of means and our distribution of proportions. How we calculate standard error changes. Now, we are only dealing with, in this course, distributions of means and distributions of proportions. But you could also make a sampling distribution out of, say, modes or medians or standard deviation itself, or any descriptive statistic. Anything you could do with these samples, any descriptive statistic you could develop from your samples has a sampling distribution. And that sampling distribution has its own standard error depending on what descriptive statistic you're distributing. So not only is there a standard error formula for means and a standard error formula for proportions, there's one for every other descriptive statistic. Now, the three that are used most common are this distribution of means that we're using, distribution of proportions that we're using, and distribution of standard deviation is actually really common to be used as well. Those of you who go on into 244 and I think it's 283 will use that sampling distribution as well. It's got some details to it that you got to mess with, but it's very similar to these. It's just a different formula for standard error. So because this is a distribution of proportions, we have to make sure we grab that tool. So our standard error here, square root of probability of success times probability of failure, or P times Q. So that's our 0.63 times 0.37 divided by 1,000. That whole thing's square root. And I can load up my calculator, but if you guys can throw out a value for that faster than the calculator loads up, that would be helpful. Oh, it should be tiny. We got a sample size of 1,000, so not surprised that that's tiny. So that would be 0.0002331. Anybody want to back that up? Oh, that's the Q is 1 minus P. I think your textbook even just likes to put P times 1 minus P over N. But that Q is just the probability of success times the probability of failure. So 1 minus the 0.63 is 0.37. So anybody back this up? I expected it to be small. That's a little small, but I expected it to be small. So it's hard to say.
I'm not getting that. How, I'm getting 0.0153. Where?
That's also small and sounds a little bit more
Too
like what
high?
I'd expect.
Yeah.
Getting 0.753.
Okay, yeah.
What was that, Andrea?
I'm also getting the 0.0153.
Okay, that sounds a little bit more what I'd expect.
Yeah.
0.01, I'm sorry, you guys said it twice.
5.3.
5.3. So the thing is I'd be careful with is make sure your parentheses, because if you divided that 1,000 outside of the radical, that would happen. So be careful about that, Allie. So just make sure that that's all happening inside the parentheses. You might even need to start a new parenthesis depending on how you write it. Because I knew it would be small, but yeah, that's a bit small. Forgot the square root. Oh, forgot the square root entirely. Okay, that'll do it too. Okay, 0.0153. So about 1.5% plus or minus. So that's going to give us an upper range of what, 64.53, and a lower range of, oops, I didn't double that. All right, I'm going to ask the calculator.
And Matt, somebody was asking about where the 0.37 comes from, which is the difference of the 100%, because you said P and Q are, yeah. Oh, you wrote it. Okay, I see. My bad.
No, that's okay. And Tessa, did that answer make sense? Good. So 0.63 plus 2 times the 0.0153. So 6606. 6606.
Okay, so.
And if we subtract instead, point 5994. So what range should our sample proportions usually fall? They usually fall between 59%, not 0.59%, 59%, almost 60%, and 66%. So that's kind of a review of our 8.2. 0.146. Right. What's the 146?
146.
Yeah, I'm not sure where that 0.0146 also is coming from. Let me know. But until that, this seemed reasonable for 8.2. Okay, good. So we talked yesterday at the end about turning this 8.2 logic and 8.1, but we'll do 8.1 in section 9.2. It's weird we switch their order. To kind of do this in reverse. This process says, okay, given a known proportion of the population, assuming we know what the population proportion is, what will our samples look like? What we want to do in 9.1 is reverse this and say, okay, if we know what a sample looks like, what does that say about our population? So we need to know an approximation for, we need to know the proportion of our population that, let's say, will buy our product. Will buy our product. We sample, let's say we go and sample 180 people at a mall or something. We find that of our 180 people, let's say 34 say they would buy. Our little product. What I'm going to put in parentheses here, should the population proportion be? Now, as we talked about yesterday, there's a good answer for this and a bad answer for this. We could go off and find out, okay, what is our sample proportion? Your book likes to use the p hat for sample proportion. So I'm going to follow that convention. That little angle or arrow on top that way is referred to as a hat. We use it a lot for vectors for doing other things, but in statistics and probability, it's for a sample value. So p hat is our sample proportion. We could go, our sample proportion is the 34 over 180. And if we turn that into a nice decimal proportion, we'd get 34 divided by 180. We'd get 0.1 and a bunch of eighths. So 0.188 repeating. So about, I'm going to say 18.89%. So our sample proportion was almost 19%. So we could say, what should the population proportion be? We could say, well, it also should be around 19%. But we know that that 19% is coming from a sample. So we know that that 19% is probably a little bit off. So we have to kind of decide, well, based on our sample size, based on our proportions, how far off might it reasonably be? Now, if we did this and got this, let's just go ahead and say that our sample proportions, let's go with 19%, just to be able to talk about it more easily. If I went and got that sample at 19% and made a claim that the population proportion is 19%, you would be very much in your rights to say, well, you don't know that. We know it should be close, but that's a strong claim off just one small sample. So you'd be well within your rights to say, no, I don't accept that conclusion. But what if I instead said the population proportion is between 1% and 99%. Now, first off, do you think that's true? Kim, do you think the true population proportion is somewhere between
Yes.
1% and 99%?
Yeah, pretty good chance.
Pretty good chance, but it's not a very strong statement. The probability is something. Okay, great. But I can be, I'm going to anecdotally, I can be like 1,000% sure. I can't actually be 1,000% sure, but I can be super, super sure it's in that range. But I'm not saying anything meaningful when I do that. Fair?
Yep.
I want something in between this. I want to have a range that's small enough to be useful, but one that I'm fairly confident in. And I want to be able to quantify how confident we are in it. So when we say this should, we want to be able to assign a confidence level to that. Now, our default confidence level is 95%. Confident. We want an interval that's not so big that it's okay, we're sure, but it doesn't say anything. I want an interval such that we can be 95% sure that that interval contains our true proportion. The nice thing is that's almost what we did up here. This usually range, this 2 standard deviations from the mean, we know that 2 standard deviations from the mean gives us that usually, and that usually is about 95%, right? So 95%, one of the reasons it's our default is because it's a nice amount of standard deviation. It's something that we're used to. So if we took this sample proportion, this 0.19, and added and subtracted about 2, notice that 2's in purple because it's going to change, about 2 standard errors, we would get a range around our sample proportion where we would expect 95% of the data to be inside. We'd expect there to be a 95% probability that our mean was in there. There are 2 issues with this. One, this 2. Because 95%, we talked about this yesterday, 95% is about 2 standard deviations. And if we're going to say we are 95% confident, I don't want to use about 2. I want to find a more precise value for how many standard deviations 95% actually is. So what we did yesterday is we used our inverse normal tool from chapter 7 to figure out a much more precise value than about 2 for what 95% or for where that middle 90% lies. You guys remember what it was? You guys who were here yesterday, which I think is Andrea, Ali, and Tessa. What did we find was the about 2? If you don't remember, that's okay. We can recalculate it. We'll have to do it for other values anyway.
And me. I need to see it.
But ideally, you guys remember doing this from chapter 7. If we've got that middle 95%, that means there's 5% on the outside. So that means there's 2.5% below and 2.5% above, right? So if we want this boundary on our standard normal distribution, we just throw in a little inverse norm with the 0.025 with a mean of 0 and a standard deviation of 1 because we're in the standard normal curve. And that's going to give us where that lower bound for 95% is. Do the same thing up here, inverse norm with the 97.5, so 0.9750 with a mean of 0 and a standard deviation of 1. That'll give us the lower and upper bounds for exactly 95%. Did any of you guys find it in your notes from yesterday? Or you can throw it into the calculator and calculate it. So the negative 1.96 and positive 1.96. So yeah, instead of 2 standard deviations from the mean giving us about 95% or 95% being about 2, the 1.96 is just a more accurate value. 2 standard deviations gives you a little bit more than 95%. That 1.96 gives us much more exactly 95%. So it's just a slight change to that 2 standard deviations that we've been talking about. Just take off 4 100ths to get it to be much more precise.
So the 1.96 is equivalent to 2 standard errors?
Yes, essentially that 1.96 is the almost 2 we keep saying. If it's almost 2, okay, what is it actually? It's 1.96. Fair?
Yeah.
So it's just a more precise version. It's like when people say, well, what's pi? Well, pi is a 30.14. Well, no, it's not. It's 3.1415.
Yeah.
I'm going to go, wait, no, it's not. It's 3.1415926. No, it's not. We can add precision to it. The 2 is a gross approximation. The 1.96 is a better approximation. And we could take more and more decimals from that inverse norm if we wanted to and get increasingly precise. Fair?
So do we use the 1.96 specifically more often for these problems?
When we're doing confidence intervals?
Yeah.
For proportions.
Okay.
We use the 1.96 for the 95.
Okay.
We still use the 2 for the usual.
Okay.
And we still know that usual is about 95%. But if we want it to be 95%, which we will for our confidence intervals, we use that more accurate value.
Okay, thank you.
Sure. Now we need to find standard error. And we had an equation for standard error, right? For proportions. It was that square root of PQ, that's a Q, I promise, PQ over N. The problem is we don't know P or Q. We know the N, we know the sample size was 180, but that P and that Q are the parameters, are the true population values. We don't have those population values. All we have is our point estimate. But here's the nice thing about proportions. We won't get this in 9.2 for means, by the way. Won't always. The difference between this sample proportion and our population proportion tends to be so small that if we use the 19% as if it was our population proportion, and thus the 0.81 for our, uh, our Q, we get a value that is so close to what our standard error should be that it tends to not cause problems as long as our sample size is large enough. Fair? So we do bring in some error in using our sample proportion, but since we don't know our population proportion, we have to. We have no choice. And this is close enough to being what our standard error is, as long as if n times p times q is bigger than 10. That's our threshold for this distribution being nice, normal, and this standard error being sufficiently close. You might remember for our distribution of means, we had to make sure our sample size was bigger than 30, right? Right? I'm going to assume you're saying yes. Had to be bigger
Yes.
than 30.
Yes.
For a distribution of proportions for binomial data, this is the equivalent. That NPQ has to be bigger than 10.
Okay.
So we might want to check that is 180 times 0.19 times 0.81. As long as that's bigger than 10, we know these tools will work.
Okay.
And it should be, is it? I assume.
Oh,
I picked that 180 to be big enough, so that wouldn't be a problem. But often 30 isn't quite enough. So often for proportional data, we need more like 50 or 60. 180 should be plenty.
Yeah. 27.7.
Yeah, plenty. Good. So having met that threshold, using our sample data is going to give us a standard error that is sufficiently close. So take a moment and compute that standard error.
So one of the gals had it, 27.7.
Well, that's
Oh, no, the other one is 0.092. I mean, 0.0292 is what I got.
0.292. Okay,
Yep, and that's what Ali got.
nice. So that's going to go there, 0.0292. And that's going to give us a 95% confidence interval. Our 95% confidence interval. I'm going to be formal here. For the true population proportion, or for the parameter of the population proportion, if you prefer, the true population proportion is whatever that ends up being.
Oh,
0.19 plus 2 times the 0.0292. Now, why did I put a 2 there? I should have put a 1.96. That's part of our point here.
oh, I did that too.
1.96. Get so used to the 2. 0.0292. It doesn't make that much of a difference, but it does make a little one. So 0.24, was it 7? I lost it.
Yeah.
2472.
Yep. 2, 4. Yep. And
And then for the subtraction, $13.28, if I round up. $13.28.
Yep.
Or from 13.28% to 24.72%.
Yeah.
Or 19% plus or minus, how much was that 1.96 times 0.0292? What was that product? How much did we add or subtract there? Yes, we will go through another one as well. So we'll walk through it. So it should be about 0.6.
0.057.
So
0.057.
and I'm gonna, or if we want to round, 19% plus or minus 6%. If we want to round fairly robustly. So oftentimes we'll get data, and usually we're looking at confidence intervals, so we want that actual interval. But in a lot of practical applications, you see it written this way. Like you watch, watch the news, and they'll say the polls say 19% of the people support this with a margin of error of 6%.
Right.
So that margin of error is the radius of that interval. It is the product of our critical value. We talked about this language yesterday. The critical value, the 1.96, is the critical value for the 95%, multiplied by the standard error. The critical value times standard error gives us margin of error. Fair?
How did you get the 0.057?
This product.
Oh, okay.
And that is something to be careful of. Very commonly, I'll have students who can find this interval no problem, but then a homework question or a quiz question or a test question will come up and say, find the margin of error.
Mm-hmm.
Well, the margin of error is just that product. They found the margin of error to do this, but not remembering what the margin of error is, that it's that product, often throws people off. So that margin of error vocabulary is something to make sure you're comfortable with. That how much am I adding and subtracting is your margin of error. Excuse me. So that 95% confidence level is going to be our default. So that 1.96 for proportions is going to be the most common critical value that we use, but we can use others and will sometimes use others. And I want to go through an example where we use a different one and kind of, as Ali, you're referring to, kind of go through the steps of a solving without kind of talking about why we're doing it. Just, well, we'll talk some about why we're doing it, but without, sidetracking into the theory. Just what would this process look like start to finish? Before I do that, any questions? Or you're like, no, we want you to do that.
Nope.
Okay. So for right now, these are going to be binomial distribution questions in 9.1. At 9.2, we'll start mixing it with means, and that's going to bring in some other tools. So right now, they'll all be proportion questions, essentially. So we will need a sample, a proportion of that sample, and then be asked for a certain level of confidence. So, say we sample, 120 people and find, Now, let's say we find only 13% watch a particular show. Watch, I'm going to say our show, the little show we're making here every day when we record this. So only 13% of the 120 people we sample watch the show that we're recording at the moment. Find a, now before we were doing, the last problem, we were doing a 95% confidence interval. And again, that's the default for kind of general use. But if you're doing stuff with medicine, especially, medicine wants to be, or like medical applications want to be more precise. They don't tend to use 95% confidence intervals. They tend to use 99% confidence intervals. They're, talking about people's lives, so they want to make sure they're more precise. People often use 90% confidence interval when precisions aren't as necessary. I've seen uses all the way down to 60% confidence intervals. I'm not sure why somebody would use 60%. That's pretty low. But if we're just talking about, how many people watch a show and it doesn't matter, 60% confidence interval could be nice. But the lowest we will generally use is 90%. We could do an 80, I suppose. We could do any percent that we want to. So let's say find a 90% confidence interval for the population proportion. So how do we do that? Step one is to check our requirements. And the big one is that NPQ has to be bigger than 10. If not, we don't know that our distribution is normally distributed, our sampling distribution is normally distributed, and using the sample proportion brings in more risk than we would tolerate. So that's the first thing we have to check. So what's our NPQ? 120 times 0.13 times 0.87. We got to figure out what that is, make sure it's bigger than 10. So take a moment, find that, make sure it's bigger than 10.
I got 13.57.
13.57.
I did too.
Good. That was close. You'll find the more extreme these proportions are, the larger the sample is that you need. So if this was like, say, 1.3%, watch our show. At 1.3%, when the slices of the population get smaller, you need larger sample sizes. Fair?
Yeah.
If it's more unlikely, so like, let's say there's like 0.5% chance of something happening. If you only sample 50 people, you might never have it occur. So the less likely it is, the more people you need to sample, and that's part of what this NPQ requirement is making sure is happening. If these probabilities are small enough, it makes sure the sample size is large enough that you will get a robust number of occurrences. Fair? So that's essentially that's the important check for us. We also have to make sure technically, make sure N is less than 10% of the population size. We're not given a population size here, so we assume, but if we're talking about 120 people, is 120 people less than 10% of people? Absolutely. 10% of people is like 700 million. So this is a technical requirement that for our purposes will pretty much always be satisfied. but you'll notice sometimes in the word problems especially, they'll tell you how many, like they'll say you sample 240 students out of a student body of 40,000. Why did they tell you there were 40,000 students? Because that 200 has to be less than 10% of the 40,000. Fair?
Mhm.
So it's not too dangerous of a requirement, but it is one that you do have to be careful of when you're dealing with small populations. What does it say? Macon? I don't know. Make that N has to be less than 10% of the population. Not going to be a big requirement for us, but it is something to keep in mind. So this check makes sure our tools will work. If this is less than 10, then our tools don't work and we stop. And instead of giving a confidence interval, we give the reply, sample is not large enough, go sample more people. 2, find the critical value for the confidence level. Now we know for a 95% confidence level, our critical value was 1.96. For 90%, we'll have a critical value, and actually we'll build up a little bank of critical values. So it's kind of nice to have a little table of them. Your book has a couple tables with some of the basic ones, like 90, 95, 99%. But we should be able to find any percentage we're requested. So again, how do we do that? Just like we did before. That's our chapter 7 tools.
Yep.
If we want that middle 90%, that means there's 10% on the outside, 5% down there, 5% up there. So I want to find the critical value for that 5%. And technically, we also want to find that critical value for the upper 5%, but it's no extra work. So it'll be just the inverse normal of the 0.05 with a mean of 0 and a standard deviation of 1. Take a moment and find that value.
I got 1.64.
1.6, can you give me a little bit more?
1.6448.
So 1.645. Now, why am I rounding that one to 3 decimals when I rounded this one only to 2? The honest answer to that is I don't know. But whenever I see the critical value for 90%, it's always 1.645, and the others are rounded to 2 decimal places instead. Every chart I've ever seen does that, and I don't know. It's just probably just because this 4.5 is such halfway in between that if you round this up to 6.5, it's a little bit too big. You round it down to 6.4, it's a little bit too small, and that they just want that extra level of accuracy. So you tend to see that as 1.645 as opposed to 1.65. Fair? I don't know what to tell you. Past that. In practical applications, that little extra little level of accuracy is helpful. Apparently.
Okay.
So that's step 2. Step 3. Find our point estimate. That's going to find the center of that confidence interval. In the problem above, we were told that 34 out of the 180 would buy our product. So we took the 34 divided by 180 to find our point estimate of 18.89% or about 19%. So we had to find it given the information. In this problem, we are just told our point estimate. Our point estimate, our sample proportion is the 0.13. So we're directly told what it is.
Okay.
Then, almost at the end here, find our standard error. Again, this is a proportion problem. So our standard error, we'd like to have them be P and Q, but it'll be P hat and Q hat because that's all we have, divided by our sample size of 120. If you don't like the hats, I wouldn't blame you, but I do want to make sure when you're reading the text and it uses the hats that you know that's your sample data as opposed to your population data. So that's going to be the square root of the 0.13 times the 0.87, 1 minus the 0.13, all over the 120, that thing's square root.
Okay.
So what's that equal to?
Let's see.
Probably 0.0. Maybe a 2, maybe a 1.
Oh, 307. 0.0307. Does that sound right?
It's in the ballpark of what I'd expect. Anybody want to back that up?
Yeah, I got 0.0307.
Okay, cool. And that's all our pieces. Then we just put it together. Put it together. Our confidence intervals are our point estimate plus or minus our critical value times our standard error. That's what all of our confidence intervals look like for proportions. And frankly, you change that P to an X bar, and it's what our confidence intervals look like for means as well. We have the point estimate, 0.13. We have the critical value that gives us 90%, the 1.645. And we have the standard error that respects the spread of our data. Confidence level, the critical value times the standard error is going to give us margin of error, 1.645 times 0.0307. We could certainly add them together all at once, but it is nice to find that margin of error just to get used to the idea that it's a thing. So 0.13 plus or minus, so that's our margin of error there. So what, it'll be 18.05% if we want to turn into percentages.
Yep.
On the high end. And what, almost 8, so 7.95%. there, right?
Yep.
On the low end. So, Ali, I'm not sure that counts as briefly, but that's it, kind of broken down into stages.
Yes, that was perfect.
Okay. And the nice thing is, you know, we'll find it for 99% as well. And once we get those three, then those are the three most common that you use.
Okay.
Your homework likes to ask things like, you know, what's the critical value for an 83% confidence interval? It makes them up. That's an important thing to know how to do. You guys know how to do it. It's just a chapter 7 skill.
Mm-hmm.
But really, it's not terribly common to do that. If you're reading a paper and the confidence interval is something weird like that, it's like they found it to an 83% confidence interval, it would make you suspicious. Like, why 83%? What were they doing to manipulate their data that they needed it to be 83%? That's a weird thing to do. Usually industries have standards. Medical industry, 99%. General statistics, 95%. Some applications, like some manufacturing applications will go 90% or even 85%. Lower than that, I start to get suspicious by nature. But if somebody's like, we have a 92.7 confidence interval, why are you making it that weird? That almost tells you somebody back-figured the confidence level that they could reach, and it just makes you suspicious.
Have you, by any chance, heard any data about the confidence levels for the antibody test? They're supposed to be so bad.
Not specifically, but because that's a medical application, it should be 99%.
Oh.
Now, the FDA would be 99%. Sometimes when the corporations are advertising, they'll use 90% because they can get away with that in advertising. So you do have to be a little careful there.
Interesting.
But if it's coming from the Center for Disease Control or the FDA, 99%, no question. If it's coming from the drug company, it could be as low as 90%. Any lower than that, and they risk getting sued for false advertising, essentially.
Okay. Oh. Interesting.
So, questions about any of that? It does take a little bit of practice. The big thing is, once we'll play with it a little bit more, and then tomorrow we'll start adding in, well, what if it's not proportions? What if it's means? And that's going to change our tools slightly. It's going to change slightly how we find our critical values. They will be close, but sometimes a little bit different. It's going to give us a different formula for standard error, like we're used to. But other than that, it'll be pretty much the same. So slightly different way to find critical values, or expected different way for finding standard error. But other than that, same process. So what we have to get good at is looking at a problem and going, okay, is this a proportion problem or is this a mean problem? Okay, if it's a proportion problem, we go down this trail. If it's a problem of means, we go down that trail.
So is this 8.2 or 9.1?
9.1.
Okay, got it.
Okay, that's actually pretty much our time today. So
thank you.
Where did the 505? It's that product. So you remember the critical value multiplied by the standard error is our margin of error. That's not how you spell margin. Margin. of error. So that's our margin of error. It's that product. Cool. It does look like a weird number that comes out of nowhere because I don't know what 1.645 times 0.0307 is off the top of my head, but apparently that product is 0.0505. Just so where that it came from the calculator technically, but as that product. And that's the same as here, that product gave us that margin of error. Okay, well, go play with these. If you come up with any questions, let me know.
Thanks.
Thank you
Bye.
so much. See you tomorrow.
Mhm.